Hello, this Science and Sport video is for Unit 7 Biomechanics, looking at Assignment 7.1, Investigating Linear Motion, and specifically on the spec, looking at A3, acceleration and deceleration. So here's the content of the spec for you to maybe have a closer look at. You can always pause the video and read through those key points. And again, you may recognize this graph from the speed and velocity previous video. This graph is a velocity time graph. It's a zero velocity line horizontally there. We've got positive velocity and change in direction velocity values below there. And these graphs are really useful to show the extent to which an object is accelerating, how slowly or rapidly it's accelerating. It shows constant velocity, motion of a steady velocity, no acceleration or deceleration, rapid deceleration, stationary object, so at the zero velocity line this object is not moving, it's still for a moment, and then acceleration or constant velocity in a totally different direction, in the opposite direction. So just that's a recap from the previous speed velocity video. Remember, above the line, positive velocity or positive direction, below the line, accelerations and decelerations in a negative direction. So the horizontal zero line there denotes which direction the object is changing velocity in. So again, there's some easy examples of, and natural examples of where we might care about acceleration and deceleration. The start of a sprint event or a race makes sense. The athlete goes from zero velocity, being stationary, and does their best to accelerate as rapidly as possible to get to peak velocity. And I guess their aim is to maintain peak velocity for as long through the race as possible without decelerating if possible. So, definitions of acceleration. Acceleration is a measure of a body or object's change in velocity in a set period of time. That's from the yellow textbook. So it's about the rate of change of velocity. You can change velocity slowly, you can change velocity quickly, and that translated means a slow or gentle acceleration or a more rapid acceleration. In many of our sports, the games that we play, we need to do short, rapid accelerations, maybe to sprint for the ball. Sorry, let's go back. The letter for acceleration is an A, and it's measured in meters per second squared. Now, time is measured in seconds. Velocity is measured in meters per second. We already know that. The change in speed or velocity over time. But acceleration is the rate in change of velocity. And it's either written as like this, meters per second, or I would suggest this meters per second squared is a more consistent unit to use. So acceleration is meters per second squared. Now, at the end of Usain Bolt's race, given he was significantly ahead and about to cross the finish line, you can see by his body language and his facial and his effort, demonstrated by his body, that he is probably not pushing as hard as he was for those last few meters. And actually, he's sort of taken his foot off the gas and is reducing his velocity. He's slowing down and decelerating. So deceleration, then, definitions. It's a description of a negative acceleration. So deceleration and negative acceleration mean the same thing. It's a measure of how quickly a body or an object's velocity is reducing. So the rate of change of velocity in a negative way, slowing down. How quickly do you slow down? Do you slow down rapidly or do you slow down gently? And again, the unit is meters per second squared. How do we calculate acceleration? Well, over here in fact, let's do the text first. Acceleration is the final velocity value minus the initial velocity value divided by the time interval that you're measuring for. So final minus initial velocity. Over here, we've got an equation version of it or a text version of it, same. So change in velocity over change in time. This triangular symbol here means changing. So acceleration is change in velocity over change in time. And this is similar to writing v minus u. V means final velocity, minus the initial velocity over the time it took. So again, acceleration is calculated by final velocity minus initial velocity over time taken. You'll need to do your own calculations and workings using your own numbers, your own sporting context examples. But here's a couple of worked examples to show you. If an object's initial velocity was 1, final velocity was 10, we do the sum 10 minus 1, final minus initial, and that gives us 9 meters per second on the top row. The time it took between those two velocity measures was 24.1 seconds. So what we're doing is 9 meters per second divided by 0.37. Divided by 24.1 gives us an acceleration of 0.37 meters per second squared. Similarly, so that is an acceleration. If the initial velocity was 12 meters per second, the final velocity was 7 meters per second. That gives us a final minus initial, 7 minus 12, gives us a minus value, minus 5 meters per second on the top row. And the time it took was 14 seconds. So we've got minus 5 meters per second over 14 seconds gives us minus 0.36 meters per second squared. So you might translate this as a deceleration. The object was going from faster to a slower velocity over a certain period of time. They are slowing down. This side on calculation 1 is going from a slower to a faster velocity. They are speeding up. That's an acceleration. Now, if we look at the value of acceleration, final versus initial, over 100 or a 200 or a 800 meter event, actually it will have very little value because any changes in velocity throughout that event will be lost amidst the overall time and the overall average value. So whilst we can get an average value, it's often more effective, more valuable, more insightful for biomechanists to look at splits, the acceleration within a smaller section of an event. So average acceleration. So if a sprinter completed 100 meters with a final velocity of 8.3 meters per second, their initial was obviously 0, and it took them 12 seconds to run that 100 meters. That gives them an average acceleration of 0.69 meters per second squared. Not so valuable, really. As I said, any changes in velocity at the start or the end are lost in that 100 meters. What you would typically do then is calculate the acceleration between distance intervals, such as every 5 minutes or every 5 meters or every 10 meters. And that data can be much more valuable to know how quick were they out of the blocks. Did they continue to accelerate for 10 or 15 meters? What point did they hit their peak velocity? Were they decelerating for the last 5, 10 or 15 meters of the race? It's obviously more valuable to understand what things to work on or to compare different athletes with their time at the blocks or their peak velocity or their deceleration at the end. Here's an example then. Usain Bolt ran 200 meters and it took him 19.19 seconds. The times for each of the 50 meter intervals were as follows. 0 to 50 meters was 5.6, 50 to 100, 4.32, 100 to 150 was 4.53, 150 to the finish line was 4.75. So they're the time intervals for every 50 meters. What you can do then is calculate the average velocities, change in displacement over change in time. So that's the whole 200 meter average velocity. His average velocity for 200 meters was 10.42 meters per second. But you can also calculate the average velocities in each 50 meters. So the first 50 meters was 8.93. The second 50 meters was 11.57, then 11.04, then 10.53. And you can see the first 50 meters was his quickest. The second 50 meters was his slowest. Slightly more interesting velocity analysis there by breaking down into 15 meter intervals. Just to finish then, this graph just shows how velocity time graphs can show the extent to which acceleration is happening. So if we look at, first of all, the blue line here, this is a linear line. With time, velocity increases proportionally, linearly. So the acceleration this athlete or object is doing is constant. They're accelerating at the same rate. Every second they're speeding up the same amount. This sort of, lilac-y colour line shows a much more rapid but constant acceleration. For every time interval, the athlete is speeding up proportionally, but at a greater rate. This pink line over here shows a non-uniform acceleration. So initially, over time, there's not a great deal of increase in velocity, but they are accelerating a little bit. At the end of this time phase here, they're accelerating more rapidly. So they're speeding up more slowly and then more rapidly. The orangey rusty colour line then just shows constant velocity. Over time, the velocity is remaining the same. They're moving at the same speed. The green line shows an initial high velocity, but that decreases over time. So they're decelerating until they cross the 0 velocity line. And then they are accelerating in a different direction. So it could be that it's a shuttle run. They're slowing down, ready to turn, and then they're accelerating away from the turn.